Okay, thanks for having me, and to the Italian audience, thanks for speaking English the last 2 days that I could follow your work. I will talk about second gradient continuum formulation for bi-pantographic fabric, a work I've done in collaboration with Emilio Barchiesi, and also Francesco Dell'Isola was involved in that. And the goal of that project, which is sort of still ongoing, is an idea that was captured already yesterday by Mario Spaniolo, to think about what a metamaterial is, and we consider a particular kind of question. So we want to have physical proof that second gradient continuum theory is required to describe certain materials. So if there are no materials existing in the environment, we must construct such materials which on a macroscopic scale, on a continuum scale, can be described by such a theory, or which require such a theory. So this is the goal, to find a certain microstructure which reveals on a macroscopic scale second gradient behavior. Well, it's quite an abstract question. So first of all, you need to know what a second gradient continuum is. And if there's a second gradient continuum, there must be a first gradient continuum. And this is the most common continuum you're used to. You can also consider it as the Cauchy continuum. So it is the standard continuum we are often working with. And starting from a variational point of view, this classification is very easy, because if we consider the special case of an elastic material, we can formulate an internal potential energy by a strain energy function, and this strain energy function depends on the material points. So it can be non-homogeneous, but also, that's important, on the first gradient of deformation. Using the principle of stationary potential energy, we will get the internal virtual work, whereas dual quantity to the first gradient of the virtual displacement, a second order tensor appears, which is the Piola stress. And working in a variational framework, we don't know yet to what kind of external actions our material can resist to. So this is something we have to prove in that framework, which is usually done by an integration by parts, together with the principle of virtual work, where we can see that the first gradient continuum can resist to volumetric forces and to surface forces. So sub-bodies interact with its complement by surface forces. This is some result we have to prove, in contrast to the way Cauchy presents the theory, where this is the basic assumption that sub-bodies interact with each other exclusively by surface forces. However, the variational procedure has its huge benefits, especially when we go beyond first gradient continuum theories, because then the only thing that changes is we just have to add another dependence of the strain energy function. So the strain energy function doesn't only have to depend on the first, but can also depend on the second gradient of deformation. And using the very same principle, not only a second order tensor will appear as dual quantity to the first gradient of the virtual displacement, but also a third order tensor will appear as dual quantity to the second gradient of deformation. If one wants to know to what kind of boundary forces or boundary actions the material can resist to, one has to do an integration by parts procedure again, it becomes a little bit more elaborate, and everybody who was today has seen the talk of Professor Rosati knows exactly what that means. We have to do twice an integration by parts. So first an integration by parts on the boundary, and then if we have some edges, we have to apply another time an integration by parts, and that's where edge forces do appear, and also the projection in, or the projection of the gradient on the surface into a normal and tangential direction. That's where new kinds of forces or generalized forces do appear, which are called double forces, which are duals to the normal gradient on the surface. This is also what we have seen in the talk of Professor Dell'Isola, starting talk of this conference. Well, if anyone wants to get a particular case of a material, we look at possibilities to design a microstructure. And for that, I also do the same thing. I start with a first gradient continuum, how a micro-macro homogenization can look like, and how it is extended to second gradient materials. So on a micro scale, we can consider a continuum as infinitely many rigid particles or rigid parts of our continuum that interact with each other. And in a first gradient theory, the position of each of all these boxes, of all these cubes, interact exclusively with its direct neighbor. For instance, by just springs. So if you formulate the potential energy of the discrete system, we will just add all the contributions of the springs, and because in the end we want to send the cubes or the length of the cubes that they become infinitesimal, we can use just first order approximation, so first order Taylor expansion. And if we do this, we will get a term here. We have the epsilon appears here as quadratic, and here are the higher order terms. And in order that the homogenization doesn't blow up, we have to rescale our stiffness parameters. So the more elements we are using, the more cells we are using, the higher the stiffness should get. And when it's using this rescaling, then we will end up with a quadratic energy in the first gradient of placement. So in a second gradient continuum, we do exactly the same, but we say that neighboring cells do not influence the position of the direct neighbors, but they influence their gradients. And one can do exactly the same approximation. Now we approximate up to the second derivative, and we have to rescale as well our stiffness parameters, and we would end up with a quadratic energy in the second derivative of the placement. However, you see here I placed some question marks between the interaction between the neighboring cells, because in the first gradient continuum we know the springs, that they interact directly with the positions, but what kind of interaction changes the gradient in the neighboring cells? And here is where the idea of a pantographic microstructure appears. And I guess all of you know pantographic microstructure or pantographs that appear in everyday life. You see here a lamp or a barrier or a fence. And if you assume such a pantograph with rigid links, and we consider this here as one cell, then the cell has, if we deform it, we change the stretch, or the stretch is given by rho, and the stretch immediately propagates through the entire pantograph because we have a lot of rigidity involved. So considering rigid bars is a little bit too drastic, or is yeah, a little bit too harsh. So what you can do is that we relax the assumption a little bit, and instead of rigid bars, we take flexible bars. And the flexible bars are represented in a discrete system by interconnecting springs. And in order to get also some bending stiffness, we add also some torsional springs in order that the system doesn't collapse. And if one does kind of an energetic homogenization procedure, which I just sketched before, we will end up with an energy that only depends on the mapping of the center line. So the only thing we need to know is how every particle on the center line deforms or maps into E2. And when considering the first derivative of the center line, we can decompose it into a stretch part and the inclination angle in case of a planar beam. And if we take the derivatives of the stretch, so the stretch gradient or the change in angle, which is nothing else but the curvature, we can see that the stretch gradient is nothing else but the projection of the second derivative of the center line, so of the second gradient, in direction of the tangent vector. And the curvature is the projection in orthogonal direction. And both these terms do appear within this homogenization process. So definitively, this is a strain energy function that depends on the first, but also on the second gradient of the center line. And keeping in mind the Euler-Bernoulli beam, which considers the stretch as an energy contribution, but also the curvature. And we see that the curvature is a projection of the second gradient. Second gradient materials are absolutely nothing new we are dealing with. Basically, it was at the very beginning of continuum mechanics that we started working on with second gradient materials. However, because the curvature takes only the orthogonal projection of this second gradient, the inclusion of the second gradient continuum completes this formulation, so that one could say that the Euler-Bernoulli beam is an incomplete second gradient material because it cannot cope with all kinds of boundary actions that would be allowed in a second gradient material. However, the pantographic beam allows for that because we have this, this direct decomposition into tangential and normal parts. So with this complete second gradient 1D continuum, we start to synthesize a planar 2D continuum. And the idea is the following, that we place one layer of pantographic beams that are horizontal, and then 90 degrees rotated, we place another layer of pantographic beams, and they are connected here that the position there must coincide at all times. And to make it a little bit more interesting, we cut out the sample that is rotated by 45 degrees. So in the end, we have now here a 2D continuum with a microstructure where in the reference configuration in D1 and D2 directions, pantographic beams are pointing. And to get the deformation energy, the strain energy function, we basically have to add up only the contributions we have already derived before. The only thing we need to accept is that these fibers are embedded in the 2D continuum. So if we project the deformation gradient F into the D1 direction, so in the direction of the fiber family 1, this, with this we can compute the tangent vector and also the normal vector. And if we want to have the second derivative in these directions, we have to project the second gradient into D1, to the D1 directions or into the D2 directions. So as before, as we had rho prime and theta prime, we now have the stretches in these fiber directions, so in one direction and in two directions. And then we add up both contributions we already had before. And clearly, this will include the second deformation gradient of the deformation gradient, so it is a second gradient material. And maybe you have seen here this additional term, which is an energy that depends on the stretch, which was not included before. And this was because in the microstructure, we added an additional spring here in these arms here that for which the energy changes when the angle changes between these arms. And this is because in the materialization of our 3D printed material, we had to include certain hinges, and maybe you see it here. The best in the middle, we have a perfect pivot. However, at the outer arms, perfect pivot would have been too small, and so we connected these little arms by just with a pin, and this includes this additional stiffness. And in order to avoid any out-of-plane buckling, we added 4 such layers, and then everything was printed with a PMMA, and then tested in a bias extension test. And here you can see the results of the experimental digital image correlation with the finite element model, which was done with a mixed finite element formulation. So we used Lagrangian elements and coupled, so Lagrangian element for the placement and also for the deformation, and we coupled it with a Lagrange multiplier field. And we got extremely good, a good match in the placements, but also in some angles we have evaluated here in the center and here at the point where we have this triangle here, and we got quite good results. Well, with that, I come to the conclusion of my talk. We synthesized with a pantographic beam a 2D microstructure that on a continuum level revealed to be a second gradient material. And we have seen that the Isola doesn't have, has a fixation on pantographs just because pantographs are so nice, but because pantographs are the essential ingredients to couple gradients in the material. And yes, we were able to materialize this microstructure continuum with 3D printing. You could claim This is not at all a material because it's way too big. It's more like a structure. However, if we make even more progress in 3D printing, I guess we can scale this microstructure down quite a lot and end up with a material that must be described by second gradient theory, also with an invisible microstructure. So thank you very much for your attention.
Are there questions from the Peruvian side, Francisco?
No other questions on the chat. No.
We have one question, Luca Placidi.
Do you have you done the identification of the stiffness matrix, for example, linearized around the reference configuration, and check if all the eigenvalues of them are positive, in order to see that all the mode of deformation are considered? I mean, even this plate is a complete second gradient.
Shall I repeat the question?
Yeah, please.
The question was if I have done a linearization of the model and checked whether the stiffness matrices have full rank, and so that the material is indeed a complete second gradient material. I haven't done that, but I can tell you immediately that it is not a complete second gradient material. It is still not, because
they are bad boys. For doing
it will come soon.
You need to do something more.
What you have to do, and this will be present next year for the Lisola, and we have to write a paper, and now it's official. You have to add a third fiber direction with for the shear. So still, if you can find some modes where the second gradient material will have no effect on the energy, and this will result also in certain boundary conditions that generally appear in second gradient materials, but which cannot be captured by that bi-pantographic fabric. This was, yeah. So this is work to be done.
There are some double faults that do not have any.
Yeah.
Before the 23rd of July, 2020.
Yes.
So thanks again, Simon.